Okay, so let me introduce the first speaker of today, Albin Grataloup from the University of Montpellier. And he is going to talk about the derived geometric perspective on the BV construction. Please.
Okay, well, thank you. So also I'd like to thank the organizer for the invitation. It's been a really nice conference. It's a pleasure to be here to talk about what I've been working on. So first of all, what I'm gonna talk about is mostly still work in progress. So there will be lots of, it's gonna mostly be around toy models and trying to reconstruct things which are already known, but in a different way, so that we can then try to generalize. But today will be very much like some toy models. And so the idea will be to actually try to understand this homological BV construction through a derived geometric perspective. So first, I'm gonna give a quick, I'm gonna try to stress on what are the aspects of the BV formalism that I'm gonna focus on to try to go toward this geometric construction. And the main one is to see this BV construction as an homological tool to handle intersection and quotients when in the construction of a reduced phase space associated to a Lagrangian. And so what I mean by that is first it's going to be about taking the solution of the Lagrangian equation, aka taking the critical locus of this functional, and in the second time taking the quotients of it by a space of solution, the symmetries of the space of solution of the Euler-Lagrange equations. And so the way it's what I want to explain today is this can be understood through two criteria how could I put it? Yeah, through characterization. It's saying that BV is kind of a derived quotient of the critical locus by a Lie algebroid of symmetries, and requiring some Lagrangian correspondence, which I'm going to define later, a Lagrangian correspondence between BV and the notion of derived critical locus of F. Through and this represents it's going to be it corresponds to the causal state resolution of the strict critical locus here. So first I will introduce some notations and what we will want this construction to look like in the end. So first, as I said, it's going to be all about toy models. So I'm working in the setting of algebraic geometry. And I'm actually gonna take a space which is going to be a smooth, affine algebraic variety over a field of characteristic 0, and F a functional. The reduced space that we want to model algebraically can be described as this space of invariance in the quotient. So the quotient would be the critical locus, and taking the space of invariance, it's taking kind of a quotient by symmetries, where I is this ideal generated by partial derivatives of F. And the way it's usually constructed is okay, it's usually given a complex where we have these causal state generators, so also known as this ghost, I guess, or no, anti-ghost here. And here there are these Chevalier-Allenberg generators, also known as ghost generator. Just tell me if I'm wrong, because I'm not necessarily most expert in this terminology. So the point is, this is exactly this causal state resolution, which was part of this Lagrange correspondence I showed before. And this will represent this, taking the invariance by taking the Chevalier-Allenberg algebra of some algebroid. Yeah. And there is some extra structure coming on top of it. So first one would be this one shifted Poisson bracket, which is given by the pairing, canonical pairing between OX and TX, and the canonical pairing between L and L duo here. We also require to have a PV charge, some element in this algebra of degree 0 that satisfies the classical master equation, which implies that the bracket with S is a differential. And one of the important feature of it is like the homology in degree 0 for that differential is exactly this like reduced algebra which I described the slide before. Okay. But now I will go toward like explaining a bit of derived geometry in order to be able to speak about all that, but in a more geometric perspective. And so I'm gonna like very roughly, not going into any details, but roughly explain the idea behind this derived geometry, who's like, it's about mixing together like geometry and homotopy theory, doing operations up to homotopy. And to do that, we need to generalize this notion of like geometric objects. So for example, a scheme, which are given by local ring space, locally modeled on commutative algebras here. To the first generalization would be derived scheme. So this time it's also a local ring space in some way, but this time we have a shift of CDGA instead of a shift of just commutative rings. And these are also locally modeled on spectrum of commutative differential graded algebra in non-positive degree. The full definition is more complicated than that, but I think it's enough to have a good picture where we replace the algebras by these differential graded algebras to have the homotopy theory coming with the differential graded algebra. That gives us more flexibility and more tools to work on. I'm going to also need a further generalization of it to do some, in order to take the invariance. And it's going toward derived stack, where this time we cannot really see derived stack as some kind of local ring space, but it's better to think of this like some functor of points of those derived scheme or schemes. So these will be just functors from the test space, so the affine CDGAs, to so the infinite category of spaces, infinity groupery, topological spaces, whichever you prefer. And the typical, what would be an affine example of it would be like this Ohm functor, where to A, you associate the functor that to every B sends the mapping space from B to A. So, okay. And okay, I hope it allows you to have some kind of rough ideas of what can these things do, but the point is really about working with differential graded stuff as geometric spaces instead of just plain commutative algebras. And I'm gonna go with a couple examples and of a derived scheme that I'm gonna use. So the first one will be like kind of what I would call a causal-tate derived scheme, where it's basically take the causal-tate resolution of your critical locus. It's a like CDGA in non-positive degree. It's a free CDGA in non-positive degree, and just take the spectrum of it, the derived spectrum, in that sense. And so the thing is like it is, as a derived scheme, it is equivalent to the critical locus. There is an equivalence of derived scheme between the critical locus and its causal-tate, the causal-tate derived scheme. And the nice thing that it provides is like, this is kind of a nice algebra in the sense it's projective, semi-free, and everything that you might want. Whereas this critical locus is a bit more complicated in some way, at least for geometric purposes. And so what we're gonna do is like, instead of doing things taking quotients on this critical locus, we can do it on the causal-tate derived scheme. Since they're equivalent, it does not really matter. But this is better in terms of like technical work or to do computational. If you want, I want to take quotients, where I don't take the tangent space tangent complex of it. It's better to use directly the causal-tate derived scheme. Okay. The second thing I'm going to need, so when I was giving my characterization of BV, that what I want to go toward, I was mentioning this derived critical locus, so now I can define it. I will define it as the homotopy pullback between the df, seen as a section of the cotangent bundle, of the cotangent stack, and the zero section here. So maybe it does not tell you much what it looks like, so I'm going to describe it in slightly more details. As a local ring space, so the underlying topological space is just the same as the topological space of the strict critical locus. It does not change anything in terms of topological space, but it changes the sheaf of rings, the sheaf of CDGA. And the sheaf of CDGA we obtain is like the symmetric algebra of the, so this denotes the tangent complex. You can just think as like the module of vector fields shifted by 1, with differential given by the contraction of df that sends a vector to a function here. And we get a few maps of like derived scheme. So the first map I defined the last slide, like this equivalence. There is a map from the causal Tate resolution to the critical locus, which basically forgets the extra Tate terms algebraically. And this typically will not be an equivalence because, I mean, this is why we add the Tate terms, is because we need to cancel lower homology. Whereas if you don't, you don't add the Tate terms, you will have lower homology. So this cannot be an equivalence in full generality. And you have the natural map to X, which is just like kind of the inclusion of a critical or derived critical locus inside X in some way. Okay. The next thing that we might need, I'm saying, okay, we are interested in taking quotient by Lie algebraids, and the question is, oh, do you see that in a geometric way? And this is something I do not have a very, very satisfying answer to as of yet, because what I'm doing is like, okay, well, if you like a way to take derived invariants when you look at an action of a Lie algebroid of some derived scheme Y is to look at its Chevalier-Lemberg algebra. You know that like H0 of this Chevalier-Lemberg algebra is going to represent this, this algebra of invariance, strictly speaking, and therefore we can think somewhat of this Chevalier-Lemberg algebra as some derived enhancement of taking the strict quotient. The thing is, it's like what I would like to understand better is like what kind of geometric object, like taking a quotient by some infinitesimal action, it should be some kind of geometric object, and how could we define it, and how could we relate it to the Chevalier-Lemberg algebra instead of just saying, okay, we take that as our definition for the quotient in the algebraic. It's something that I think deserves further investigation, understanding this thing. Okay, now I have like the way of defining most objects, like derived scheme that's going to be involved in the construction, but there's also more structure on it. There's this like shifted, -1 shifted symplectic structure that appeared, this Lagrangian correspondence, and this is what I'm going to try to define very quickly from now. So first thing, I'm going to recall the definition of the cotangent complex, which I denote LA, which is a derived version of taking the module of differential forms, the module of Kähler differential form in the algebraic setting. And it's as simple as applying omega-1 to an appropriate resolution of A. So typically A might not be somewhat nice enough. For example, if it's like the functions on the strict critical locus, it's going to be a quotient. It might not be projective. It might not be somewhat well behaved enough. So you might need to take a resolution of it, and then you apply the differential functor to get the cotangent complex. So this is like the thing that you would like to see as like these one forms, but it's a bit more intricate than that. And if I want to speak about 1 form, 2 forms, 3 forms, I need to speak about this Durham complex. was quite a bunch of structures. So the derived complex, so it's technically it's called it has the structure of a graded mixed complex. It's given by like derived global section of this symmetric algebra, as you might expect. But since Lx is already a complex itself, this has a degree n, and you can extend the differential on Lx to the whole symmetric algebra by derivation to get this vertical derivation, which I call delta. The second thing you have symmetric powers. So it gives you some overgrading called the weight, P, defined just by you take the P symmetric power of Lx. And, and you have the mixed differential, which is exactly what you would expect from the derived differential. It increases the weight by 1, so you go from P forms to P plus 1 form, and you have a shift in to make it coherent with the conventions taken here. Okay, so this complex with these two differentials, it's like a graded mixed complex. And at some point, I will need to speak about the derived cohomology. And the version in this setting of it would be taking this total derived complex, where you take the product of all the weight P parts of the derived complex, and you put on it the total derivation, which is the sum of the derived differential or the mixed differential plus the vertical one. So that's gonna be something that I'm gonna need later. Up. So, sorry. Now I can really define P form. So as you can expect, like I'm not gonna only ask for what is the definition of a P form as an object, but I will want a full space of P forms, so that points are P forms, and you have lines in this space where they're going to be homotopies between P forms, and then homotopies between homotopies, and so on, so that we can still do things up to homotopy, as we want to when working in this derived setting. And so a P form of degree n, well, of course, you're going to look at like the weight P part of the derived complex. You're going to make an appropriate shift, so you see that when you unpack it, you get this Q symmetric thing shifted by n, which is what you might expect. And it is a complex for the vertical differential, only for the vertical differential. And you take the geometric realization of it to obtain a space, whatever this means. So, but like the thing that it brings is like a P form of degree n, a point in this space is gonna be given by like one of these global sections in the appropriate degree, such that delta of omega equals 0. So there is this extra condition that might not be immediate if you think of it's not just a section in the P skew symmetric product of the cotangent. And now I also need to speak about closed P form, and this is somewhat a little bit involved because then you will need a condition on the derived differential of your P form, omega 0 here. And which this condition is going to be given by some P plus 1 form and some P plus 2 form and P plus 3 form that will have to satisfy some conditions altogether, which I'm going to explain. But the way it goes is like, okay, you take all P plus I form of degree n minus I, and on that you will put the total differential, delta plus d derived, and take the geometric realization of this, this new complex. So even if you don't understand necessarily this definition, a nice way of viewing it is like a point in this is going to be a closed P form of degree n is given by some omega, which is the sum of omega 0, omega 1 plus something, with omega I being a P plus I form of degree n minus I, such that delta of omega 0 is going to be 0. So omega 0 is actually going to be in the space of P form of degree n because of this condition that I told before. And also the omega I plus 1 or omega I for I greater than 1, they are controlling the derived differential of the omega I. And the nice way of saying it is like the derived differential of omega 0, it's like exact. And the exactness condition is for the total differential, and the exactness condition is given by the omega I for I greater than 0. And this gives, actually, this is exactly, this thing is exactly the data of a homotopy between the derived differential omega 0 and 0 in this topological space. Okay. So now I've like, it's like a bit some technical definition for it, but like the point is like up to replacing something, some equality by some homotopies, or up to instead of having quasi-isomorphism, it turns out that everything is more or less the same. And this is what's going to happen when I'm going to just redefine like symplectic structures, Lagrangian structure and Lagrangian correspondences. And it's just going to be about changing strict things by their homotopy version of. So in that mindset, n-shifted symplectic form, omega, it's exactly a non-degenerate closed to form of degree n. So closed, it's already homotopy something, because I've already defined it just before. And non-degenerate, it's like the underlying 2 form induce a quasi-isomorphism here. And as I say that, like, it doesn't, this approach does not change much on the theory. Like 2 typical example would be first, the n-shifted symplectic structure on this n-shifted cotangent stack here. It's like the canonical well, just like what you would expect. And the derived critical lattice I define is also -1 shifted symplectic. And it's like, it's also fairly canonical in the way that it really comes from one canonical shifted symplectic on the cotangent stack. Okay. Now I'm gonna go towards Lagrangian. So like, instead of having a Lagrangian as a subvariety, I'm gonna speak about Lagrangian for all morphism from L to X. So if you could think that it's just an embedding, a close embedding on L into X. And what would it be? First, it would be, okay, that, well, the symplectic structure restricted to L should be 0. And in our case, so that's an isotropic structure. It's like saying that there's a homotopy between 0 and the pullback of the symplectic structure on L. Okay. And of course, if we want it to be Lagrangian, we'll ask some non-degeneracy condition, which I do not want to get into much details, but can be phrased into 2 ways. Either we get like a sequence which is null homotopic thanks to gamma here. And this non-degeneracy is saying that this sequence is fibered. Or if you're more familiar with it, you can get a quasi-isomorphism from the tangent complex to the conormal with the appropriate shifting. Okay. And from that, I can finally define Lagrangian correspondence, which is where I wanted to get to. So a correspondence between X and Y via the, some L. So you have a diagram like this, with X and Y are n-shifted symplectic. And it's the data of a Lagrangian structure from on the map from L to the product of X and Y, where this is undone with the symplectic structure given by omega X minus omega Y. This is why I put that bar, because I put the opposite symplectic structure on it. And this basically means that, well, the pullback of omega X is homotopic to the pullback of omega Y, and you have some non-degeneracy condition associated to it, which I will not go into more details. And yes, these having Lagrangian, like having Lagrangian correspondences is something that can compose with something that behaves very well. And this is like, yeah, this is what I'm gonna use in order to express like this, to express the idea that this BV is some kind of reduction of the causal-tate or the critical locus. Okay, So now, if you have been a bit lost by all this derived geometric stuff, which I felt was needed to understand that I'm actually doing something, I'm going back to like working on BV, and now I'm going to try to explain what how am I actually going to construct BV using some of this formalism. So first, I'm going back again to say, okay, what do I want to have from this? I want to construct a space of BV complexes whose points are given by, well, quotient of a critical locus value algebroid. I'm a bit repeating myself, but it's just to set the ideas. I want a -1 shifted symplectic on it. I want it to have a correct cohomology, of course. I want it to be quotient by some maximal symmetries in some way. So which can be phrased by saying that the algebroid will subject to the kernel of the differential, which we can think I can have a algebroid of maximal symmetry. That's the most natural way to describe like symmetries of it. And something that I've not quite worked out, but I would like to understand how to understand A as some kind of reduction of this critical locus in this setting. So what I'm actually going to use, so that's what I was saying, is like these two things, that BV is quotient of the Koszultech resolution derived scheme by the algebroid of off-shell symmetries. When I'm working with on-shell symmetries, I do not know if I can recover the correct cohomology typically. So this is a kind of technical condition that I need to put to compute the cohomology in this case. And I'm requiring this Lagrangian correspondence. So now this is all defined. So, and when I'm going to try to show all the requirements I had using this space, we'll see that this is what would encode this idea of maximal symmetries. This is what should somehow encode this idea of reduction, even though I cannot explain it fully yet. But this is, even though it might seem a bit mysterious, this is what gives, this is really what makes, allows to recover the usual BV complex. So, but first I need to define the space, and for that I need some technical tool given by the Grothendieck-Lurie construction, which basically I'm gonna take a functor from some infinite category to the category of like infinity groupoid or spaces. And I'm gonna obtain a co-Cartesian fibration, whatever that means. What I'm gonna be interested in is from some new infinite category to C. And this is the category that I'm going to be interested in, and I'm going to try to describe it a little bit. So how to describe it is like objects are going to be by a pair of some point A. And to A, you can associate like a topological space F of A, and a point in this F from unstraightening from Lewis terminology. A point in this is going to be so A and some X in F of A. A couple like this. And a morphism will typically, to B and Y, is going to be the data of some F, a morphism from A to B in the underlying category C. Given this F, you have a morphism of topological space F of F from F of F to F of B, who's going to send X to F of X. And to complete the morphism, I need some alpha here. So it's given by F from A to B plus some alpha from F of X to Y in this category N of F. This is a very rough picture to have an intuition of what what's going on in here. And now, so I'm gonna define my C to be the full subcategory of like the RAS cap under KTF. So basically, all quotients, these A's will be, these algebras A, which are quotient of KTF by some Lie algebroid of off-shell symmetries. And they sit always under KTF through the natural projection. And we can define a functor from this C of two spaces that sends such a morphism to the space of Lagrangian structure between P and I with a critical locus as I pictured before. And now, using this functor, we can define the space of BV complexes as this unstraightening the Grothendieck construction of this functor. And to tell you that it's actually what I want, like if I use what I explained just before on the Grothendieck construction, objects in there are going to be given by first something in the base, so some A, which is a quotient Chevalier-Allenberg algebra of some some algebroid L prime on KTF. It's also going to be the data of some -1 shifted symplectic structure and a Lagrangian correspondence between A and the derived critical locus. So basically, I'm just saying that the object are exactly the object that I wanted from the beginning. So this is this construction that gives it, but it also gives how to understand morphism between them and all the homotopies and homotopies for free. Okay. So now I'm going to try to explain how to recover the BV complex from an object in there. I'm going to take an object in this BV and say, okay, does it actually look like what we want it to look like? And the first thing we'd get is like a point A in there will always be equivalent to some semi-projective CDGL like this. So a few things, like we can say that like the differential with Tx and L, it's the Koszultai differential, and this is exactly the Chevalier-Allenberg part of the quotient. We just need to be a bit, so there are some technical thing because we need to be careful with what type of algebra we take. We need to be careful of how we can take resolution of the algebraic by cofibrant thing to make it work. And there are some technical things. So per se, as stated, this is not quite true. There are some technical restrictions, but which are not really restrictions when it comes to actually computing, constructing the usual BV complex. Like the usual construction of BV complex will fit within these technical conditions, which I'm not getting into here. So we get like a first occurrence here. The problem is a priori, L prime has nothing to do with L. So, but this is where like the Lagrangian correspondence kicks in. Like using the non-degeneracy of a Lagrangian correspondence structure, we can show that L is quasi-isomorphic to L prime. So this implies several things. Like first, like if you think of the anchors, since this is quasi-isomorphic, in some way the anchor associated to L prime will be somewhat the same as the anchor, some anchor associated to L, but this anchor is kind of the same as the natural map from L to Tx1 in L2 to Tx1 in this complex. And because of the Koszultai resolution is defined, it needs to be acyclic, and it implies that this L will surject onto the kernel of the differential, so that it is acyclic. And in some way, this will imply through this equivalence that this will have to surject into the kernel of the differential too. So this is the way that the Lagrangian correspondence implies that we are actually going to take quotients by some maximal symmetries. Okay. The next thing is like understanding the symplectic structure once we have this form, and the isotropic structure and the non-degeneracy condition imply that both the two forms, the underlying two forms, both going to correspond to the pairing between these two. When you do the I mean, you can show that it will correspond to the pairing, but like on the symplectic level, you can phrase it in like using the symplectic structure. But yeah, it's going to be the canonical symplectic structure on this side of thing, and it's going to be the pairing of L and L prime. When you go when you use phi on phi dual to go from L and L prime, from L to L prime and L prime dual to L. You use them to pair the two together. Okay. So it looks a lot like this, like the BV complex I described at the very beginning, except for this prime. And still, we know that L is equivalent to L prime, is quasi-isomorphic to L prime. So it would be nice if we could just, like, through this quasi-isomorphism, replace this L by L prime. And this is actually possible. So you can, it requires some homomotopy transfer of Lie algebroids. So it's like, there is quite some technique behind this, this thing. It's not just like, use it, you need to transfer the Lie algebraic structure so that you have the right, you have an equivalence, but also for the correct differentials and not just for like some linear version of it. But the point is you can get such an equivalence here as CDGAs. And the symplectic structure on it is exactly the one that we expect. In particular, it corresponds to this non-degenerate one-shifted Poisson structure that I described at the beginning. Something I did not mention here, but like this, like I'm always speaking about the underlying two form here. And I'm not speaking about like these homotopies, the closed structure on it. And this is actually some part which is kind of a technical problem, because a priori it has no impact on the BV complex and everything that we want to, but there could be this extra structure here that's there and it's completely useless and can be kind of annoying. This like, so just mentioning that like I'm always speaking about the underlying two form when I'm in all that I'm doing here, but the rest does not impact what I'm trying to explain. And well, this is just saying like the way that you can compute the cohomology of A is the same as what you would do for like the standard BV complex. So you use this spectral sequence technique, and you first compute the causal-tight differential, the causal-tight resolution, and then you will have some remaining term, delta 1, which will correspond to taking this invariant thing. With further work, you can show, so this is like this corollary that depends, that I can only do for like this off-shell symmetries, and I do not know if how to do it for on-shell symmetries typically. So I expect it might work, but it would require like some more thinking for general symmetries. Okay. And the last thing I want to mention, so far I have like something Poisson, symplectic, I have a CDGA, but I a priori do not have a BV charge. So it's a bit like the opposite way of the way BV is usually constructed. Usually it's like, okay, I have a graded algebra, I put a Poisson structure on it or a symplectic structure on it, and then I use that to define a differential through defining the BV charge and obtaining requiring the classical master equation. Here, I already have a differential, but a priori, I do not have a BV charge. And this is what I'm going to try to explain in the last slide, is like how to obtain a BV charge. So how to show that this differential is Hamiltonian, actually. So a way to show that something is Hamiltonian is like, I'm gonna need to go through these polyvector fields. So it's basically saying in the algebra of the differential graded algebra of polyvector fields, being Hamiltonian, it's like when a deviation is exact. But in these polyvector fields, I do not really know what to do. And I want to transfer this problem to the derived algebra. But I can do it by contracting derivations with the underlying two form. And this gives an isomorphism between the polyvector fields and the derived algebra here. This isomorphism goes through the totalization. And like exactly what I'm saying, like a derivation in here is Hamiltonian if it is exact. And so I'm going to ask myself, okay, the contraction with omega 0 here, is it going to be exact? This is like the question I'm going to try to answer. And it's actually a bit simpler in here because of like this proposition where like saying that you can find a strong deformation retract between the total derived complex of A and the total derived complex of the Koszultait resolution. But the thing is, A contains, J is just the same thing as KTF plus these Chevalier-Limburg terms. And P infinity has the nice property is will somehow forget these Chevalier-Limburg terms. And now asking whether this contraction is exact in here is the same thing as asking if P infinity of it is going to be exact for this strong deformation retract. And like the last thing I want to mention is like this is actually the case. And it's even nice because P infinity of this contraction, it's exactly D the RAM of F. It's very simple. It cancels a lot of what is complicated. And this shows that the differential that we had on our complex is Hamiltonian. And it even gives like some kind of formula for the BV chart where it's F plus this H infinity defined before of this contraction of delta with omega 0. So, and this is kind of the way I wanted to go to. So now, like one of the consequences, and so this corollary is technically wrong up to this irrelevant close term, but this kind of shows up to dealing with these irrelevant things that BVF is connected. This kind of goes back to the uniqueness of the BV complex, and some other thing is like in usual construction often there are like you can try to identify different the different terms in the filtration of construction of your BV charge with like the different perturbation of H infinity and of delta according to some filtration according to like these Chevalier-Limburg terms. So you can read the terms of the BV charge using this like perturbation lemma and the different term like the different expansion of these things. So I think it's I've finished it. So thank you for your attention.
Thank you very much for this great talk. Yeah, are there questions? Okay, we have one question from Yuchi. Oh.
Hi, yeah, thanks Albin for your talk. Am I correct in understanding that your goal is sort of the following? So you sort of want to give an interpretation of a BV complex as arising from taking derived symmetries of the critical locus.
Mhm.
I'd
like to have. I'd like to say, oh, the BV complex is like, for example, a symplectic reduction of the critical locus, and tying that in the derived sense would actually give directly a way to construct it somehow. This is what I'd like to say.
I see. And there's also a sort of reverse perspective. You start with symmetries, take the derived quotient, and take the derived critical locus of that. Is that related to your approach, or are you trying to do?
I mean, this is
the opposite perspective.
So this is an interesting question too to explore. There was this paper not long ago from Kalak and Anel where they did this thing for groups and like with these shifted momentum maps. And I think maybe there could be some extension for algebroids and some things to be done in that direction. But I do not, I mean, I think I do not understand fully enough this quotient by algebroids for now, so that I can make a statement in that direction, trying to say, okay, that's the same thing as doing the reverse, or does the reverse give something else, etc., etc. So these are very interesting questions, and again, this is like work in progress, and this is certainly in the direction that we'd like to get toward at some point. Yeah.
Okay, thank you.
Okay, then we have a second question. Please.
Am I unmuted? Yeah. Hi. Yeah. Thanks, Albin. Was very nice. So when you compute the BV cohomologies, I would like to understand how general this result is, because that you say you don't have cohomology in negative degrees.
It's actually very general.
Examples to that.
I've not proven it precisely, but I think that if you just take a quotient by a Lie algebroid such that it factors through the kernel of a differential, maybe you need to be injective, something like that, then you will necessarily have the correct cohomology. It might not be symplectic because it's not going to be a Lagrangian, etc. But I think this computation of the cohomology method is like fairly general.
You say that the A in BVF has cohomology, trivial cohomology in negative degrees. So this is in undefined degrees or in ghost.
Yes.
Undefined.
In positive degree, it can be something else. In 0 degree, it's like what you expect with taking all these like little restriction of shell symmetries and so on. But like the theorem, okay, I can go back to it. The theorem itself here, it's fairly general. To get back here, it requires a little bit more work because it requires this factorization through the kernel of df to work it out correctly, so that it's actually like the invariant through all of the ideal of the symmetries. But this is very general, actually. This is a very general result. Like if you take a quotient of consultate and you try to compute, you will get something of that form, yeah. And it's going to be acyclic in negative degree. But it's just spectral sequence arguments, like it's really nothing more than that. Does that answer your question?
Yeah, I'm not sure, because I mean, when you take something super simple without symmetries, say take a scalar field or something like that, then when you have 0 modes, then I think you have something like cohomology in negative degrees.
Can I maybe say something to this? Because I think this is actually just compatible with the Felder-Kazhdan axioms of the BV theory, that the negative degree in BV cohomology vanishes. I mean,
it's not like I'm asking it as an axiom, but like I think I get it in.
No. I'm not. No. This is not a. I mean, it's just called Felder-Kazhdan axiom. But there's a paper where they prove this.
Okay. I mean, this is one of the paper I've like looked. Yeah. This is the paper classical master equation that you're referring to.
Yes. Yeah. Yes,
okay,
exactly.
Then these BV algebras are different to the ones, say, Costello-Quilliam produce.
Yeah, I have to say I'm not sure at the moment. So I mean, it's just like this is like this statement of the negativity of the the negative degree. These things vanish. This is definitely something that can be found there.
But for a derived critical locus, that is not true in general. As far as I see.
Yeah.
Anyhow, maybe I chat later with you, Albin, because I would like
that
to.
would be interesting. But we need to
the-
know what you're talking, because I'm not sure I know what. I've never. I mean, I don't know. I've not seen much of applications, but like I do not know of any PV construction with homology in negative degree. At least none that actually could compute also the homology in degree 0. So it's like always a problem.
Maybe because you say you don't know any, let me say that there is this construction of Getzler where he looks at a one-dimensional theory of the Brink-Schwarz particle, and there actually the -1 cohomology survives. And this is actually something very special, because as you say, usually it should vanish. But this is also a recent paper, actually. I mean, recent years. So I mean, he like Ezra says that he doesn't understand why this is the case. So yeah. Anyway.
Okay, thanks.
Thank you.
Okay, so if there are no further questions, let us thank Alba again. And let's take a 5 minutes break, and see you afterwards.